Welcome to the channel. Today we delve into a future that promises to revolutionize every aspect of our existence through the words of one of the most authoritative and recognizable minds in the world of science, Dr. Michio Kaku. Renowned theoretical physicist, co-founder of string field theory, author of several New York Times bestsellers, scientific correspondent for CB This Morning, and host of numerous specials for BBC TV and Discovery Science Channel, Dr. Kaku holds the Henry Samant Chair in Theoretical Physics at City College of New York. His voice reaches millions of people through his weekly radio broadcast. What follows is an account of his extraordinary vision on quantum computers, as he shared it in an interview with Big Think. But before we start, don't forget to subscribe to the channel and activate the bell. By doing so, you'll support my work and allow me to create more and more content like this. And now, hold on tight, because here we go. According to Dr. Kaku, digital computers have already radically transformed our lives, but the arrival of quantum computers will be an even more historic event. We are, in fact, in the initial phases of this next revolution. We are talking about a new generation of machines, the ultimate computer, capable of calculating directly on atoms, the ultimate constituents of matter itself. Who is involved in this race to perfect quantum computers? All the major global players, says Kaku. If the main technology companies don't participate, Silicon Valley, for example, risks becoming the next Rust Belt, an industrial area in decline. But the interest is not just economic. Anyone interested in security, from the FBI to the CIA up to national governments, is following this evolution with extreme attention. The reason? Quantum computers will have the ability to decipher almost any code based on digital technology. In Kaku's vision, these computers will change everything: the economy, the way we solve problems, even the way we interact with the world. They are destined to be ubiquitous. Dr. Kaku guides us through the three fundamental phases of computer evolution. The first, he explains, was the era of the analog computer. It takes us back 2,000 years to the discovery of an incredible device in a shipwreck, the Antikythera mechanism. It was, in fact, the first analog computer in the world, designed to map the movement of the moon, sun, and planets, simulating the cosmos. Subsequently, with the prosperity of civilization and the need to count herds, profits, analog computers were based on sticks or bones. This phase lasted thousands of years, up to the work of Charles Babbage, who created the definitive analog computer with hundreds of gears, levers, and pulleys. By turning a crank, one could calculate longitudes, latitudes, and even interest rates, a very valuable tool for the banking industry and commerce. The digital revolution arrived with World War II. Babbage's machine proved too primitive to decipher German codes, a task that fell to mathematicians like Alan Turing. Turing codified many of the laws of computation in what is digital today, based on the transistor. These operate on zeros and ones at the speed of electricity, and every modern digital computer is at bottom a Turing machine. The next step, beyond digital computers, is the quantum era, as Kaku points out. Quoting Richard Feynman, one of the founders of quantum electrodynamics and a true visionary, Kaku explains that Feynman wondered how small a transistor could be made. And he realized that the ultimate transistor is an atom, a single atom that could control the flow of electricity, not only in an on or off state, but in everything in between. That's why, according to Kaku, we need to move to quantum computers, computers that calculate on atoms, not on transistors. Kaku reminds us that transistors operate on zeros and ones, but subatomic particles can do much more. These particles actually act as waves and can be in multiple states simultaneously. And to describe the waves that make up a molecule, a new mathematics is necessary, and it is precisely here that quantum computers come into play. If you want to delve deeper into these topics, like superposition and the wave function, watch the video you see above. The extraordinary computational power of quantum computers derives from the fact that electrons, on which they are based, can be in multiple places simultaneously. It is this, Kaku states, that gives quantum computers their power. They calculate not only on a single universe, but on an infinite number of parallel universes. At a fundamental level, quantum mechanics, as Kaku explains, can be understood through the analogy of Schrödinger's cat. You put a cat in a box, is it dead or alive? Until you open the box, you can't know. It exists simultaneously in a state of being alive and dead, a superposition of two different states. In other words, the universe has divided into two. In one half, the cat is alive. In the other, it is dead. This is the basis of quantum theory. Until a measurement is made, the object can exist in any number of states simultaneously. The cat could be dead, playing, jumping, sick, anything. This concept summarizes the power of quantum computers. They calculate on these parallel universes, and that's why they are so powerful. But how much faster are quantum computers compared to digital ones? Kaku explains that digital computers measure their power in bits, so either spin up or spin down, 0 or 1. A large digital computer today operates with billions of bits. Quantum computers, on the other hand, use qubits. A qubit doesn't just represent spin up or down, but everything in between, all the infinite possibilities of an object between two states. The latest generations of quantum computers can model thousands of qubits, and the goal, according to Kaku, is to reach 1 million. He underlines that we have already passed the point where a quantum computer can outperform a digital one on specific tasks, the so-called quantum supremacy. We are not yet at a machine that can outperform any digital computer in general, but as Kaku states, we are very close. The number one problem that quantum computers must face, according to Kaku, is decoherence. Since everything is based on particles like electrons, which have associated waves, when these waves vibrate in unison, it is called coherence, which allows quantum calculations. But if this coherence is lost, the waves begin to vibrate at different frequencies, generating what is called noise, interrupting the calculations. To contrast this, it is necessary to reduce the temperature to almost absolute zero, an environment in which everything vibrates slowly in unison, an extremely difficult task. However, Kaku notes how nature itself has already solved this problem. Photosynthesis, for example, is a quantum process. Mother Nature manages to create coherence at room temperature, proving to be even more intelligent than us when it comes to quantum theory. Despite the challenges, Kaku emphasizes that the obstacles to the development of quantum computers pale in comparison to the benefits they could unleash. We are about to open the floodgates of innovation. Consider agriculture, for example. The green revolution that allowed us to feed the world's population is coming to an end. With quantum computers, we could unveil the secret of how to produce fertilizer from nitrogen more efficiently, revolutionizing agriculture. In the field of energy, Kaku suggests that quantum computers could be able to create fusion energy, stabilizing superhot hydrogen inside a fusion reactor. And medicine? Life is based on molecules, and diseases like Alzheimer's, Parkinson's, or cancer are beyond the reach of digital computers. But quantum computers are made for this. They will be able to model diseases at a molecular level. That's why, as Kaku hopes, we can cure the incurable, radically transforming medicine. Finally, Dr. Kaku's personal hope for quantum computers is that we will be able to create a theory of the entire universe, the theory that eluded even Einstein, the one that would explain black holes, supernovas, and galactic evolution. These equations are so complex that no one has managed to solve them with current means. Perhaps, Kaku concludes, They will be solved in the memory of a quantum computer. In summary, in Dr. Michio Kaku's vision, quantum computers represent not only an unprecedented technological leap, but a unique opportunity to redefine our relationship with knowledge, disease, and the universe itself. It is an exciting future that is taking shape right now, molded by the most brilliant minds in physics. If this journey into the world of quantum computers, through the words of one of the greatest scientific minds, has fascinated you, leave a like and a comment with your opinion, and don't forget to subscribe to the channel so you don't miss the next videos. See you at the next video.